Okay, this is problem, and we have audio. This is problem number 3 from the AP problems, and it's an electron initially moves in a horizontal direction, has a kinetic energy of 2 times 10 to the third electron volts, which means it's been accelerated through 2,000 volts, right? When it is in the position shown above, which is right here, halfway between those, right? And it passes through the uniform electric field between 2 oppositely charged horizontal plates and a field-free region, region 2, before eventually striking a screen. We're not actually going to go there, 0.8 meters from the edge of the plates. The plates are 0.04 meters long, are separated from each other by a distance of 0.02 meters. The potential is 250 volts across them, right? Gravity is negligible. Calculate the initial speed the electron enters as it enters region 1. Right, and then this one, for this one, we're going to do EV is 1/2 mv squared IM. I'm talking to the camera, right? And this is an actual formula in the data packet. It comes from work is or change in potential energy, right? Is change in voltage times charge. So that is that, and then this is just, of course, kinetic energy, right? So 1.602 E negative 19 coulombs. It's been accelerated through 2,000 volts. Right, and a volt coulomb is a joule, right? And then 1/2, and the mass of an electron is 9.11 times 10 to the negative 31st kilograms, and then V is what we don't know, right? Okay, so I'm going to calculate that square root of 2 times 2,000 times 1.602 E minus divided by 9.11 31st, and I'm getting that the velocity is 2652174.3.04. So that's 1, 2, 3, 4, 5, 6, 7. 2.7 times 10 to the 7th meters per second. So that is definitely less than the speed of light. So we're in good shape, right? And then it says calculate the magnitude of the electric field between the plates. For the electric field, so this is A, right? B, the electric field is just V over X, right? So it's 250 volts divided by 0.02 meters, and that's going to be a lot. 250 divided by 0.02. And that is 12,500 volts per meter, or newtons per coulomb. Okay, yeah, there we go, right? Calculate the force acting on the electron. Okay, so that's C, right? Well, if E is equal to F over Q, then F is EQ. So that's going to be 12,500 newtons per coulomb is what I'm going to write, right? And then Q is 1.602 E minus 19, right? Okay. So I'm going to go second entry, store that in V. Okay, so I've stored this number in the variable V, and I'm going to store this number, 12,500 times 1.602 E negative 19. So this is 2.00 times 10 to the minus 15 newtons. I'm going to store that in F. Whoops. I actually stored that in cosine. Okay, store it in F for force. Okay, so that's part C. Part D says sketch the path of the electron in regions 1 and 2. Well, it's an electron, so it's negatively charged. It's going to follow a path like that. I don't know what the displacement is, right? And then in the second region, it's just largely going to go straight because gravity is such a small acceleration. This is going to be a huge acceleration. Okay. And then it says calculate the vertical displacement of the electron as it passes between the plates. And the answer is something like 0.0025 meters upward, right? So let's calculate that. The next thing we're going to have to do, so D is to sketch this. It curves in here. I'm trying to draw a parabola there. It goes straight after that, right? And then E. Before we do E, we've got to find the acceleration. So acceleration is F divided by M. I'm using F equals ma. Right? So this is the force. So 2.0025 times 10 to the minus 15th divided by 9.11 times 10 to the minus 31st. So divided by 9.11. And this is 2.19813 times 10 to the 15th. Right, and I'm going to store that in alpha A. Right, and now we're set. We can horizontal, vertical. Horizontally, it's 0.04 meters. Vertically, we don't know. We can't say that it's 0.02 because we don't know that it goes that far. That's just how big the plates happen to be. But initially, this is 0. This is upward 2.19813 times 10 to the 15th. Right, and we've stored that in A. Horizontally, the velocity is 2.652 E7 meters per second, and that's the same as this. This guy's 0, right? So the time is going to be this divided by this, right? So alpha V, where is alpha V? Did I have that there? Yes, I do. So 0.04 divided by alpha V. Time is very small, right? 1.508 E minus 9 seconds. That castles across. 1.508 E minus 9. And now we can figure out the displacement here. So the displacement here is going to be, I'm going to use UT plus 1/2 AT squared, right? So basically it's just 1/2. The acceleration is here. Right, and then it's this time. Am I off the page? No. Okay. 1.508 E minus 9. I'm right there. I'm right on the edge. I'm living on the edge. Okay. So this is AT squared. So I'm just literally going to go 0.5 alpha A times alpha T squared. Oh wait, hold on. I have to store that in alpha T first. There we go, okay. So 0.5 times alpha A, alpha T squared. And the answer is somewhat surprising, 0.0025. Like it just comes out even, freaky. Okay, and then if you were going to figure out where it hits the screen, you would have to figure out where its position is right here, right? It's going to be just slightly changed, right? And then what this velocity is, what this velocity is, right? Essentially, it's just going to go in a straight line like that. I'm not going to do that because I'm going to hit this button.